So today I'm going to talk about probability and some things I find very interesting about it. And then I'm going to go on to like Bayes' theorem, the birthday paradox, and just some things I find interesting with probability. So to get started, what is probability? Well, probability kind of goes with statistics. And what is statistics? Statistics is the logic of uncertainty. And math is the logic of certainty. So we're trying to quantify uncertainty. So there's a thing called a sample space. Let's just say this is our possible sample space. And we're going to be looking at an event. So this is sample space and an event. Now, all events happen in the sample space. All right? Now let's give a very basic definition of probability. The probability of A happening is equal to the number of, let's say, good outcomes. Out of all outcomes. So that is the basic definition. There's other ways and better definitions of it, but that is a very simple one I don't want to start with. Let's get rid of that. So let's look at probability. Let's say everyone knows flipping a coin. That's usually the first thing. Well, you have either heads or tails, right? If you flip a coin, you have 50% chance that it's heads, 50% chance that it's tails. Alright. So the probability of flipping heads, well, you want to get heads. So you have a probability of getting heads and tails. So you have two. Now, all outcomes is going to include the good outcome as well. That can kind of get confusing. Sometimes you get to bigger and bigger and interesting sets. But that right there is the logic on it. So let's say, what is the probability of flipping, let's say, heads? Let's get rid of that. What is the probability of heads and tails? So let's just create a matrix out of that. You got heads, you got tails, you got heads, you got tails. Coin one, or let's just say coin two. You got a 25% chance of heads. You got a 25% that it's a heads and then a tails. Tails, heads, or tails, tails. Now, I like it a little darker. Okay, I can maybe edit that out. Now we got this right here. Now I'm not saying that heads has to come first or tails. I'm just saying to compare the things we're looking at is the heads and the tails. So, first question is what is the probability of that? Well, we're not giving that there has to be a heads then a tails. We're saying if just the mix of any of them. It can be a tails heads or a heads tails. So that would be a 50% chance of that happening. Now you could get tails tails, which is a 25%. Now let's say the order did matter and you wanted heads tails, well then that would be a 25% chance. 25 for all of those. Okay, we got that. Now let's say what's the probability of getting 10 heads in a row? Well, first the probability is you have two outcomes. There's 10 of them. And you want the probability, how many of those are going to be heads? So that's going to be 2 to the 10, which is 1,024. So the probability, or the odds of you flipping a coin 10 times and getting all heads or all tails or any other mix of those preset is going to equal that. Now that's one of the things that matters. Where do you start? Where is your set going to be? Let's say you have heads, tails, tails, heads, tails, tails, heads. Alright, you got 9 right there. What's the probability that the next one is going to be tails? Probability that this one, the 10th one, is going to be tails. Now let's say you're just looking at what is the probability that this will be tails in this set. Well, that is a 50-50 chance. But let's say you have this. What's the probability that you're going to have all these the same? What's the probability that you're going to have a heads, tails, tails, heads, tails, tails, heads, heads, tails, tails? That is going to be the same probability as getting all heads, because you're already setting where you want it to be. With this, you're picking way at the end. Like, what's the probability of this one? Well, what's probably that single one? Well, that's just going to be, you have one favorable outcome, that tails, heads are the outcome, so you have a 50 chance on that. But on the other one, if you want all these to be known from the beginning, it's going to be those odds. All right. So let's say I'm a fan of football. So where's my eraser? I can leave that up. So let's say you have the probability of the 49ers going 16-0 in the season. Now, there's a few things we're going to have to take into account here. Let's say that we're only looking at wins and losses. Ties are not going to be a thing. We're not going to worry about the tie. We're just going to look at wins, losses. Well, we can look at wins, losses. You might think that it's a different game, but it's basically the same logic as heads and tails. Now, there's a few other things I'm going to have to throw in here. All teams have the equal probability of winning. 50-50. All teams are the same. Same probability of winning. 50-50. All teams are equal. What's the probability that the 49ers can go 16-0? Well, you have wins, losses, so you're going to have 2 to the 16, which is equal to, I believe, 65,536. If I do believe so. I'm going to take 2 to the 16. Yep, that is right. So the probability of the 49ers being 50-50 for all teams going undefeated is that right there. Now, of course, in real life, not all teams are equally likely. Some teams might have a 30% chance of more of winning or whatever. And other teams will have a lower percent chance of winning, so you have to take that into account too. But just taking any NFL team, given even probability, even odds of winning, the probability of going 16-0, 16 wins, is 1 over 65,536. So pretty crazy odds. Now, there have been undefeated teams, but again, not all teams are like this. If you have a team that has a higher probability of winning and other teams have lower probability, then you can calculate that out. But that goes into a lot more mathematics. Now, I think that's pretty interesting, looking at future events. It's where you want to set up if you're looking for futures. I can erase this. What do I want to go to next? Let's go to let's do the birthday paradox, actually. And this goes into combinatorics or whatever. I think that's how you pronounce it, combinatorics. So what is the probability of you, how many people will it take to be in a room to have the probability over 50% of somebody landing on the same day as you for a birthday? So let's look at this. You're looking at a birthday. Let's just say, it's 365 days. It's equal to a year. We're going to take out leap years. We're going to take out twins and all that stuff as well. What's the probability of, how many people do you actually need to be in a room to get the probability to be above 50%. So has the same B-Day as somebody else, not as you, has the same B-Day. So there's a few ways to do this. It's kind of hard to calculate out. You might think, well, do you need 100 people? Do you need 180 people to get above 50%? Do you need more than that? Do you need less than that? Do you need 30 people? How many people do you need to have the probability of one of those people having somebody else's birthday? So let's just use extrapolation methodology. Let's say you're in a room. What's the probability of you having a birthday that matches somebody else? Well, that's not going to be. You're going to have 365 over 365. That's you. You're going to have one day on that. The next person, though, let's say we're trying to, well, the best way to do this is actually to calculate what is the probability of not having the same birthday. So that's you. There's no way you're going to have anyone else's birthday. If you walk into a room, you're the only one there, you're not going to share anyone's birthday. Now, let's say another person walks in, and so he will have 364 outcomes out of 365. So the probability of him actually sharing your birthday is very, very low. If you were to calculate that, that would come out to 0.997, I believe. Yep. Which you can then go to 99.7% that they do not share a birthday with you, which makes sense, right? There's a possibility that you have the same birthday, but there's 364 days that your birthday does not fall on the same day. All right, and let's bring in somebody else. And you keep doing this and doing this and doing it. But then let's say you have 23 people. That's actually how many it takes to have a probability of falling on the same birthday above 50%. And it may seem a little weird, because I know it does for me. When I first, I'm like, 23 people? That doesn't seem right, that there would be 23 people to get a probability above 50% out of 365 possible outcomes. But our minds are really bad at looking at the comparative. Because when I think about this, I think of my birthday, minus that off 22 other people are gonna match with me. But they're not just matching with me, they're matching with each other as well. It's not just me. So, for this, which basically would be 365 over 365. And of course, in this, you're going to be timesing them together. There's a multiplicative rule in probability, is you times them together if they're different. So, and this is going to go all the way to, what was that? Let me go to 342. Out of 365 will end up giving you if you times all those out, all the numbers between there, you're going to get 0.4927, which basically would be 49.27% that none of those birthdays match. Because that's what we're looking at. None of the birthdays match. So So then we're going to take this number and we're going to minus it against 100. Now why are we doing that? This is the probability that no one is matching. We want to find the probability that someone matches. So if you have 100, and we're going to minus that 49.27, you're going to get 50.73% that somebody's birthday will match with 23 people. All right, now another way of looking at it, so you have a group of 5 people, right? 5. Let's do 1, 2, 3, 4, 5 people. And all those people are connected to other people. So you can have a connection here, you can have a connection here, you can have a connection here, you can have a connection there. I'll do just a different color. This person can have a connection there. Well, that one's already taken up. You can have a connection there. You can have a connection there. So blue. This person can have a connection here. You can have a connection there. Because these other connections are all taken up. Now this person, you can have a connection over there as well. So to calculate that out, if you wanted to do that, that would be 5 times 4 divided by 2, which would then come out to 10. Possible. So let's say you had 10 people, you can do that 9 divided by 2, which would you end up getting 45. And then let's say you have 23 times 22 divided by 2, which would then come out to 253. Which is what we're dealing with over there. So you're going to take that, because you have 23 connections, but you're going to times that by 22 people. So that is an interesting one, the birthday paradox. Our minds are not good at picking up probabilities. I mean, when you first think of like, there's 365 days in a year, what is the probability of somebody having your birthday or anyone else's birthday in that group, you would think, you know, heck, you need a lot of people. But when you get up to about like 70 or 80%, you're basically, or 70 or 80 people, you're basically at like 99.999% accuracy on that. So yeah, if the number of people equals 50, probability of that being would be 97%. You're taking 50 people times 49 divided by 2 are the outcomes. Now, of course, someone's got to match the other, but the probability of one of those people having the same birthday is 97% out of 50 people. 50 people out of 365 days, which is crazy. Crazy. At least I think it's pretty interesting. Now we're going to go on to the important one, Bayes' theorem. Alright, so Bayes' theorem is the probability of H given evidence is equal to the probability of E given H times the probability of E all over the probability of E. Which this probability can be equaled out to the probability of H times the probability of E given H, right? Probability, yeah. Plus the probability of negative H times the probability of E negative h. So this is how it works. Let's say you get a disease that affects 0.001% of the population. You might think you got this disease. And you end up getting a test done. And the test is 99% accuracy with 1% wrong on the test, 1% failure on the test. Now, what is the probability that you actually have the disease you were tested for? So the probability of, let's say, disease in population is equal to 0.001. Now the test you take, probability of the test being true is equal to 99%, then the probability of the test being false is equal to 1%. Now, if you were to ask somebody, what's the probability of you actually having this disease? Well, most people would say, if I test positive, I'm really bad. I have 99% or somewhere around there, a high percent chance of having this disease. And what Bayes' theorem tells us is it tells us that that's not really true. So I'm just gonna hold this in my hand. So in here, this is right here is that you would test positive if you had the disease. This is the prior probability of having the disease. This is having the test and correctly having it. This is not having the test and wrongly identified. And this is the probability of the test being true. So let's plug in those numbers. So you would have 0.99 times 0.001%. The reason you have that is the probability of the population having that, let's just say 1,000 or whatever. So then you're going to have that over. E as well. You're going to have 0.001 times 0.99 plus 0.999 times 0.01, which then if you were to calculate this out, you would get 0.00099 all over, well, this is going to be the same as that, just reverse, but it's timesing, so you're good. So that's going to be 0.00099 plus 0.00999, and if you were to add those together, I'll just go over here. This would then go out to 0.00099 equaling 0.01008 which would then go out to 0.98126. Oops, it's in the wrong spot there. Now if you're going to do that in percent would equal 12, so equal 9% chance of having the disease. So the probability of H given E is equal to 9% chance. So this is pretty interesting. So there's a disease in the population. It affects 0.001% of the population. The test is a 99% accuracy with a 1% failure rate, or it gets it wrong. Now, you get tested for the disease and it says you have this disease. But the actual probability of you having the disease is 9%. Now, why is this weird? Well, it may seem odd, and we're not good at this. But let's say you have 1,000 people. You know, you have 1,000 people in this little town. And 0.001% of the people in that town have it. So that would be one person has the disease. But 99% of the time it is right with guessing it. But 1% of the time it is wrong. So that would be 10 people out there will falsely be identified. Now, as we had earlier up on there, it is the probability of the favorable outcomes over all probabilities of the outcomes. So you're going to have one person who actually has it, but 11 people who are tested of having it, and 10 who actually didn't. Now you can rewrite this saying that the one person who has it, for one person who has it, plus the 10 who don't have it. Now if you do that and divide that, that is 9%. Now this right here is pretty interesting. But let's say that you end up taking the test again. This shows why you should always get a second opinion on a test. Let's say after having that, you go see another doctor with a 9%. So the numbers for this would end up being that 0.99%. But here you're going to change that. You're going to change that to the 9%. So percentage you can put as point there. You're going to times that again now. As the other time, this is going to be flipped to 0.09 times 0.99 plus it's going to be 0.91 times 0.01. So that if you calculate this outward, you'd end up getting 0.0891 divided by 0.0891 plus 0.0091. Then end up calculating that all the way through. You're going to get the probability of H given evidence is going to come out to 0.90733, or the probability of H given evidence is equal to 91%. So I'll do that. Probably. So the first time you take a test, for a disease or anything like that, and you get 9%. Now you go to another doctor and you get tested and it's positive like the previous one. That jumps up to a 91%. And Bayes' theorem shows us why that is true. And this is why you should always get a second opinion. I mean, that is a huge jump right there. Let's see, was there anything else? You have to remember your priors is a big thing. Base rate neglect. Another thing you should do is imagine your theory is wrong. And this kind of goes into just logic right here. So Bayes like playing this game of like, let's say, you're turning your back to a pool table and somebody takes the ball and they drop it. And you have to calculate where it is. And the other person throws balls randomly and they're like, oh, it's to the left. So they'll drop one ball, let's say that's the main ball we're gonna work off of, to throw another ball, and Beige will be like, oh, well, what is it, left or right? It's left. Okay, well, all right. I'm gonna write that down, and then 5 more balls go into there to the right. So what's the probability of space? Just write that up here. It'll make more sense. Let's just have a. Oops, so let's say a random ball is thrown, and let's say it lands here. Let's just call that A. Then every other ball, we're trying to figure out where A is. So let's say another person throws a ball and it lands over here. And then you'll say, where is it due to A? Is it left? It's to the right of it. Okay. Someone throws a ball again, it's like it's to the right, to the right, to the right, to the right, and then it's to the left. So you'll know the ball is on the left side of the table. I don't know how far left it is, but you can, the more evidence you get, the more information you have, the better decision you can make about the whereabouts. Now you can also break that off and, go here. You can have 1, 2, 3, and 4. Is it left in quadrants and stuff like that, and slowly figure out more and more where the ball is located to the information you just get. So on the first one, you can say, hey, the ball is to the right of it, and you're like, okay. And then another one gets dropped, it's like it's still to the right, still to the right, still to the right. And it looks like in this little thing here, it looks like 2 balls are to the left of it, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then 13 balls are to the right of it. So you can start to get where it is, and you think, what is the probability of the balls if they're falling randomly? I must be way on the left side of this table if there's only 2 balls here. Now you can figure out, well, after an infinite amount of times, you'll figure out where you are. Another way you can think about this, let's say you've been in a cave your whole life, and you get out of the cave and you see the sun rise. And then you ask yourself, does this occurrence happen all the time, or is this just a one-off? Is this just a quirk? Does this always happen? So your idea of how often does this sun actually rise, you don't really have any other information, but you did see it one time rise and set. But you don't know if this is a constant occurrence or if this is just a sin down experience. Like an eclipse. You see an eclipse happening, like, oh, you get out of your cave, you're like, oh, you see an eclipse. Well, does this eclipse happen every day? Is this just a one-off? Then the next day happens and there is no eclipse. Okay, well, maybe tomorrow there's going to be an eclipse. Maybe, no eclipse is the one-off, is the random thing. Well, I shouldn't say random, but is the less probabilistic outcome. And then you keep going and going and going down this road, and you start to realize, hey, it's been, one day of this event, and 96 times, it's been different. So I guess I should put more weight into that time it happened 96 times. Which is another interesting way of looking at it. But is a way you can look at how you can use Bayes' theorem every day-to-day life. There's also a thing called Gittins index, which is pretty interesting. I probably should have done a thing on that. Okay. I could just talk about it. I don't have the equation in front of me. It's a more of an elaborate equation, but the basic logic of it is, let's say you go to, there's 2 restaurants. Restaurant A and restaurant B. Restaurant A, you've been there a total of 8 times. This is a restaurant you've been to. This is a restaurant you've never gone to before. You've never been to that restaurant. But restaurant A, you've been there 8 times. So let's just break this off into a table. Oh, that light keep going down. That light keeps going out a little bit. Alright, so you break this off into a table. We're gonna say good, and we're gonna have bad. So out of the total, for good, let's say you had 6 good experiences and 2 bad experiences. You know, the food wasn't as good. Maybe it was bad and you got sick after. It just wasn't a good experience. You had 2 of those. Then you had Gittins index. Can I have that on there? So you have that 6 good experiences, 2 bad experiences. You put this into Gittins index. This will come out to let's just have Gittins index on the bottom there. All right, let's start closing this off so it looks nicer. Absolute beautiful. Goddamn, I am an artist. Let me tell you that right now. I am just Picasso. I don't even need that one at all, but oh well. Let's just leave it the way it is. All right, so you have that. That will end up giving you a Gittins index of 0.84. Now, the question you ask is, what is the Gittins index of restaurant B, a restaurant you've never been to? Now, if you think about it, what is the probability of a restaurant you've never been to? Well, it's either good or bad, right? It's either going to be a good experience or it's going to be a bad experience. Let's take neutral out of it. Let's see, it's either good or bad. Now, you would think, well, it's probably a 50-50. It's probably a 50-50 chance. So probability of me is, 50%, 50%, which this has a 0.84% on Gittins index of happiness scale or whatever you want to call it for that restaurant. So there's no point in me going to this new restaurant. But Gittins index ends up coming out with this at a 0.87. Now that's interesting. Why is it interesting? You would think it would be a 50-50, but there's a beautiful logic underneath. Let's say you end up going to the restaurant and it's bad. It wasn't good at all. It was an awful experience. Maybe the food wasn't good and the bill was super high and the service sucked and it took forever and it just smelled weird and it just wasn't a good time. You don't have to go back there. You're done. You've already went there. But let's say it's a good experience. In fact, it's a great experience. In fact, you just found out a new hangout place, a new place to go get food. Well, that's not just a one-off. You can keep going there again and again and again. So when you think of something, we don't look at the long-term implications of it. We look at it kind of narrowed down. It's either going to be good or it's going to be bad. Well, if it's good, you're going to go there more often. So you have time is a factor. And actually, I did find the equation of this, which is just right here, which is VI. R, which is the summation of t minus 1, t equal to 0, beta t r c t c. And I mean, you can do this for movies as well. Let's say you're on Netflix, you're on Hulu, you're on Disney Plus, and you're searching through, and you're like, well, what should we watch? And you're constantly through there, you're going up and down, paradox of choice. What if there's something better? If I keep moving to the right, or if I keep going up and down, is there going to be something better that pops up? Paradox of choice, which is interesting. I should probably do a video on that as well. But it's actually better for you to go and see something else. Now, this does take into something. This does take in that time is equal to or close to infinity. Now, we can change that to infinity being your life. So let's say it's your last time in this town where you've lived for 10 years, and you have a choice of going to restaurant A or restaurant B. Now, those numbers would be different. And here's why. You go to restaurant B, and it's a bad experience. Well, why did we go to this restaurant? This is my last time in town here. Why didn't we go to that Italian place I like? Why didn't we just go there? And which has always been better. Let's say I've been there, 100 times and only 2 have been really bad. So 98 times were fantastic, 2 times were awful. Why did we go to this new restaurant? And that would be a huge, huge minus on the happiness scale. But then let's say you go to that new restaurant and you absolutely love it. It was frankly the best food you've ever had. The experience was fantastic, just amazing, amazing. Well, now you're thinking, I've been in this town for 10 years and I've never been to this restaurant. And the last day I'm in town, I go to this amazing restaurant I could have been having for the past 10 years. Oh, what an idiot. What an awful thing. I can't believe I had this amazing thing, but now I just don't have it anymore. Ugh. So it's actually detrimental if your time is very short for that. Let's say, you're with some friends and you're not going to see each other in a long time. It's like, hey, are we going to watch this classic movie that we all love? Or are we going to watch something new and take that risk? It's better not to take that risk. Now, if this is a friendship you're going to have for the next 10, 20, 30 years, hopefully, yeah, watch something new. This also could go into to dating as well. Actually, a guy who came up with this ended up creating a equation. He was figuring he was gonna date till he was 35 years old and stuff like that. And he ended up calculating, well, hey, the next person I meet, I'm gonna marry them. And this goes into another mathematical thing I could probably get into. That's another thing I was gonna talk about. Yeah. But yeah, this is Gittins index. It's pretty interesting. It takes time into consideration, so it's something very useful. Let's say you're young and you were driving, let's just say Mazda. You've been driving Mazda, and that's all you've done. And now, a few years go by. Let's say you're 34, you're looking to buy a new vehicle. It's like, you know what, I'm going to change it up. I'm going to go with Hyundai, or I'm going to go with a Ford, or I'm going to go with a Chevy, or something like that. And you change it up. I would say that's a good thing. Give it a shot. Give it a try. You may not like it. Maybe you should just, lease it for a little bit and not actually buy it. And that goes into different things right there. But yeah, I think it's a very interesting trade-off you can have there. And very good to think about. Very useful as well. Very useful as well. All right, now the last thing I'm going to talk about is the Monty Hall paradox. And then I'll probably quit with probability. I'll just get a drink here. Alright. So this is how it works. The Monty Hall was a game show. So you have an option of picking 3 doors. Now, out of these are amazing doors. I am a great artist, if you couldn't tell. Just goddamn Picasso. So there's 3 doors. You have an option to pick a door, but the game show host says, hey, one of these doors has $1 million. Let's just have money signs. And 2 of the other doors don't have anything. Just absolutely nothing. Alright, so what is your probability? Well, your favorable outcome, like earlier, your favorable outcome is that $1 million. But there's 2 bad outcomes, so a total of 3 outcomes, 1 favorable. So you have 1 out of 3, 1 out of 3, 1 out of 3. And now let's say you pick a door, and let's say you pick door 2. Let's just have say you pick 2. And the game show host says, great, you picked 2. Let's open up door number 3. Now, he's going to open up the door that does not have the prize. If he does, that's going to take away the suspense. You know, you're going to want later on to know. So he opens up door 3, and it's got nothing behind it. Now, your probability of winning, if you pick door number 2, your probability of winning before that door was opened, probability of win is 1/3. Now he opens up that door, there's 2 doors left, and he gives you an option. You can stay with the door you got, or you can jump over and go, you can go to 1. So this is the door you're on. You're on that right now. You're on that one. And now you have an option to jump over. Well, what are the probabilities? Do you think now, well, at first there were 3 doors. Now there's 2 doors. So you have 1 favorable outcome out of 2. So you would say it's, 50-50 basically. 50% chance of getting that $1 million. It's a lot closer than 33% chance, or 1/3. But does your probability change if you jump over to door 1? Or is it the same? Or does it not matter? Is your probability better staying? Is your probability better switching? Is your probability best, what's your best probability? Now most people, when I first thought of it, when I first read about it, I'm like, oh, it's 50-50. So it doesn't really matter. But that isn't true. If you actually were to switch, your probability of winning is 2/3. Of switching. And you have 1/3 of staying. That doesn't seem right. There's 2 options. Why is this one if you switch over, a 30 or a 66% chance of winning, and this is a 33% chance of winning? How is this so much greater? Why is that? And when I first thought about it, I'm like, there's no way that's right. That doesn't seem right. But when you first picked it, you had 1/3, 1/3, 1/3. He ended up opening a door he knows doesn't have the prize. So it doesn't have the prize. So you're taking that out. But when you first picked, you had a 1/3. Now there's 2 left. In the beginning, there was 1/3 chance for both. Now there's two. You'd think it'd be a 50-50, but it's not. The probability moves over here. There is deeper math I could go into. I don't have the solution. I could probably work it out, but there'd be a lot of stumbling involved. But this is a very interesting one, and it's sort of had, I forgot what year it came back in, but it was with a lady who had like a very high IQ and stuff like that, and she said she would switch, and then a lot of mathematicians were like, oh no, that's not true, blah blah blah, but it is. If you switch, you have a 66% chance of winning. You could also, they've done this with envelopes and stuff of that nature. But yeah, I think that's a very interesting with probability. I don't fully know how to explain it, but I think it's a very interesting one. It's called the Monty Hall problem. Yeah, that's basically everything I want to talk about probability. So I kind of want to, my next video will probably be about mixing in game theory with psychology, looking at like, let's say, what's the probability of this thought happening given, let's say, mere exposure, availability heuristic, and self-fulfilling prophecy. And then you can go into the nature-nurture argument with that as well. Probably the nurture is going to play more due to the mere exposure, the availability heuristic, and the self-fulfilling prophecy all in play. But looking at things of that nature and then adding in probabilities and then game theory on top of that, which will be interesting. But yeah, hopefully this was something interesting. Hopefully I didn't butcher. I probably did butcher some stuff. But yeah, I think this is some interesting stuff. But yeah, I think that's all I got. Is there anything I left out? I don't think so. Oh, actually, I did. So going back to Bayes' theorem and how to think. This actually can happen in every day-to-day life. And I want to talk about the Dreyfus Affair. Now, Dreyfus was a French officer in the late 19th century. And he was accused of selling military secrets. This was the late 19th century in the Third French Republic. This is in 1895. Now, Dreyfus, he was a French officer, or a French general staff guy, and he was accused of selling military secrets. And they kind of put him on trial. And they started going through, and someone would say, Dreyfus, he's very smart. He's a very smart man. Spies need to be smart, because spies, they need to know a lot of stuff. So this right here is evidence that he is a spy. He's very smart. He must be a spy. They also said that he was very tidy. He kept things in order. Yes, a spy needs to keep things in order. I mean, he's a spy. He's, taking documents and stuff like that. He needs to keep things tidy. And they came up with all this stuff about him, saying that, yes, this is absolute evidence for this. A spy would definitely do this stuff like that. All of his teachers said he was gifted. Yes, spies definitely need to be gifted. They need to know a lot of things and go through life in a lot of scenarios. They need to be quick on their feet. And Dreyfus ended up getting accused. Now, he was a Jew, and there's a lot of anti-Semitism going on, which is this. The Dreyfus Affair is a very big thing in history. Emile Zola ended up writing J'accuse, which in French means I accuse you. He wrote articles criticizing the French military, stuff like that. And anti-Semitism was growing. Then you have Herbert Herzl, who came up with the theory of Zionism, which is basically the idea that Jews need a homeland, somewhere where they cannot be accused and stuff like that and seen down as and stuff of that nature. But it is an interesting one, sort of in Bayes' theorem, and looking at how are you looking at this situation. Is this evidence? You can kind of build evidence for anything. You look at lists of, I believe there was something like 948 reasons why 9/11 was an inside job. And which is called a gish gallop. When you throw so much at somebody, you can't, refute all of it. You have to break it apart and do each one bit by bit. But yet that takes a lot of time to do. I assure you, a lot more time than the person who came up with that did. So I think that's where probability can definitely help in the thinking part of it, the logic part of it. But yeah, I think that's everything I wanted to throw out. And again, with that Dreyfus and all that stuff, it goes into nationalism and ideology and stuff like that, but which I should definitely do in a different video. But it is interesting how you can take sort of mathematical frameworks and put them into a logic set that you can kind of use for your day-to-day life. But thank you very much.